Welcome! Today, we're going to break down electrical resistance. Now, on the surface, it seems pretty simple, right? It's just the opposition to current flow. But underneath that, there's a really rich story about how electrons move, about material properties, and about a famous law that, believe it or not, is more of a guideline than a rule. So let's jump right in.
All right, let's start with a core question. When you apply a voltage across a component, a certain amount of current flows. But that relationship isn't random. It's controlled by a specific property of that component. So how do we actually describe and quantify this opposition to the flow of charge?
And the answer, of course, is resistance. But in physics, we can't just leave it at that. We have to go deeper than a simple definition, V divided by I, and really understand what's happening at a microscopic level inside the material that gives rise to this property.
Okay, so here's the formal definition you'll see in textbooks. Resistance, R, is the ratio of the voltage across something to the current flowing through it. The unit is the ohm. But this is just what we call an operational definition. It describes what we measure for a specific component. The real physics, the fundamental property, is one level deeper.
And this is a super critical distinction to make, resistance versus resistivity. Think of it this way. Resistance is an extrinsic property of an object. It depends on its shape and size. Resistivity, on the other hand, symbolized by the Greek letter rho, is an intrinsic property of the material itself. It doesn't matter if you have a chunk of copper or a long, thin copper wire, the resistivity of copper is a constant. It's the true measure of how much a material inherently fights against current flow.
So let's take that idea and apply it to a real-world component. How do we combine that intrinsic property, resistivity, with the extrinsic factors like shape and size to figure out the resistance of an actual object, like a piece of wire?
Let's look at this simple model of a resistor as a cylinder. The formula here tells the whole story. The resistance, R, is equal to the resistivity, rho, times the length, L, all divided by the cross-sectional area, A. And this just makes perfect physical sense, right? If you make the wire longer, the electrons have to travel farther and bounce into more things, so resistance goes up. If you make the wire thicker, increase its area, you're basically opening up more lanes on the highway for the electrons, so the resistance goes down.
Now, when you're drawing circuits, you'll see a couple of different ways to represent a resistor. In the US, you'll typically see the ANSI standard, which is that zigzag line. Internationally, you're more likely to see the IEC standard, which is a simple rectangle. They both mean exactly the same thing.
As a practical matter, when you pick up one of these common resistors, you're not going to see its value written out in numbers. Instead, you have to read the code, this standardized system of colored bands.
And the system is actually pretty easy once you get the hang of it. The first two bands give you the first two digits of the number. The third band is the multiplier, basically how many zeros to add. And that last band tells you the tolerance, or how precise that value is. But enough about that. Let's get back to the physics.
Okay, this brings us to one of the most fundamental relationships in all of circuit analysis. It's the thing that neatly connects voltage, current, and resistance. It was first figured out experimentally by the German physicist George Simon Ohm way back in 1827.
And here it is, Ohm's law. What it says is that for many materials, especially metals at a stable temperature, the voltage across them is directly proportional to the current flowing through them. That famous formula, V equals I times R, tells us that the resistance, R, is a constant. It doesn't change no matter what voltage you apply, and it's this constancy that makes Ohm's law so incredibly useful.
Now, this is a point I really want to drive home. Ohm's law is not a fundamental law of physics, like, say, the laws of gravity or thermodynamics. It's an empirical model. It's an observation that just happens to work really well for a certain class of materials we call ohmic. But as we'll see, tons of modern electronic components are specifically designed to not follow this law.
So how did Ohm actually show this was true? And how could we prove it for ourselves, right here in the lab? Well, let's take a look at the classic experimental setup.
Verifying Ohm's law is actually pretty straightforward. You need a variable voltage source, so you can change the voltage. Then you need an ammeter, which you place in series with the resistor to measure the current flowing through it. And finally, you need a voltmeter, which you place in parallel to measure the voltage across it.
So you set that up and you start taking measurements. You dial up the source voltage a bit, record the voltage and current. Dial it up some more, record again. And when you plot all those data points with voltage on the y-axis and current on the x-axis for an ohmic device, you get this beautiful straight line that goes right through the origin. This is the experimental proof of Ohm's law. And the slope of that line isn't just some abstract number. That slope, the rise over the run, or the change in voltage divided by the change in current, that is the resistance of your component. So for this particular experiment, the slope tells us the resistance is 3.84 ohms. Pretty cool, huh? This linear relationship is fantastic for analyzing simple circuits with resistors. But what about all the other stuff? What about the countless modern electronic components that don't follow this simple rule? So what does that VI graph look like for a device that's specifically engineered to break Ohm's law? Let's take a look at a classic example of a nonlinear, non-ohmic device.
Let's consider a diode. A diode is a semiconductor device, and its whole purpose is to act like a one-way valve for electrical current. We can use the exact same test circuit as before to see how it behaves when we apply both forward and reverse voltages. And whoa, check out this IV curve. It looks nothing like the straight line we saw for the resistor. It's fundamentally non-ohmic. When you apply a reverse voltage, almost no current flows. But when you apply a forward voltage, once you get past a certain threshold, about 0.7 volts for silicon, the current suddenly takes off and increases exponentially. This is the classic behavior of a diode, and it's completely nonlinear.
And this brings us to a final, really important takeaway. The V equals IR formula that we all know and love is actually a macroscopic, simplified version of the law. Ohm's original, more fundamental insight was microscopic. It relates the current density J to the local electric field E through the material's conductivity sigma. This version connects the bulk property we measure directly to the physics of electrons bumping and drifting through the material. It's a great reminder that the simple circuit laws we use every day are really just the emergent behavior of a much more complex and fascinating microscopic world.